Okay, on to section 2.5 and continuity and actually an application of limits. Okay, now we saw in section 2.2 that by Dr. Bob's anthropomorphic definition of limit, a function f defined on an open interval about c, except possibly it's c itself, has limit L, denoted limit as x approaches L of f of x, limit as x approaches c of f of x equals L. Anthropomorphically, if the graph of y equals f of x tries to pass through the point c comma L. So in that setting, it didn't matter what happened at x equals c. As long as, whatever this means, tries to pass through, as long as the graph of the function tries to pass through the point c comma L, then the limit exists. And what tries exactly means we spelt out in great detail with the epsilons and the deltas. Now we're looking at something different. We're going beyond limits and looking at continuity. So in this topic, we are going to be interested in what happens at x equals c. Limits unaffected by what happens at x equals c. If the function succeeds in passing through the point, fails to pass through the point, doesn't matter in a conversation about limits. But we're talking about a new topic now. I warned you in the past, there'll be something in the future coming where whether it succeeds or fails in passing through a point matters, and it's the topic of continuity. So we consider an idea different from the existence of the limit, but related to it. Existence of the limit will be part of the idea of continuity. Informally or anthropomorphically, f is continuous at point c if f tries to pass through the point c comma f of c, and it succeeds. And notice the L value has been replaced with a function value from what we had up here. CL has become CF of C. So in saying that, we're saying the function's defined at C, and the value of the function equals a limit. In other words, anthropomorphically, the function tries to pass through some point, and it succeeds in doing so. It matters what happens at x equals c now, because now we're talking about continuity. Limits are part of the story, but they're not all of the story. And we have a formal definition of limit, so we can state a formal definition of continuity. We'll do that first and then look at it a bit more informally. We'll treat interior points differently from endpoints of a domain. We might have a left endpoint of the domain, in which case we'll require the function to be defined on an interval of this sort, starting at left-hand endpoint A of the domain. We might have a right-hand endpoint B of the domain, in which case we'll require the function to be defined on an interval of this form. So we're requiring the function be defined at certain points, that's new, and close to those points. Close to from the left or close to from the right when dealing with endpoints. Otherwise, we'll just be dealing with the defined on an open interval containing C, including C this time. So the function has to be defined at C for it to be continuous at C. Okay. Definition of continuity at a point, a function, y equals f of x, is continuous at an interior point C of its domain if the limit as x approaches c of f of x equals f of c. So implicit in what's highlighted there is that the function's defined in an open interval containing c, except possibly c itself from the limit part. On the right-hand side, we explicitly talked about f of c. So what's implied there is that indeed this time the function is defined at c as well. In terms of endpoints of the domain, we'll make the following definitions. The function y equals f of x is continuous at left endpoint A, or continuous from the right. We'll have a picture to elaborate on this left-right stuff here in a second. Or is continuous at right endpoint B, or if you like, continuous from the left at B, if the following one-sided limits hold. And here's our picture. So A, here's a picture. A is a left-hand endpoint of the domain. So when we graph the function, it say starts here and it ends over here. Here we'll require a limit as x approaches a from the positive side of f of x equals f of a. Here we're requiring a limit as x approaches b from the negative side of f of x equals f of b. And we get pictures that look like this. So interior point C, something between a and b in this picture for the graph of y equals f of x. Think of it as the function tries to pass through this point C comma f of c, and it succeeds. That's the anthropomorphic way to view it. That's what the graphs look like when a function is continuous at an interior point. Over here at this this left-hand endpoint of the domain, we take a limit from the right. Left-hand endpoint, right-hand endpoint. So you take, as it were, limits from inside the interval a to b. So we'll take x values greater than a that approach a, x values less than b that approach b, because that's where the function's defined. So think of the function coming in from the right to this left-hand endpoint, trying to pass through. It's a one-sided limit, probably trying to contain is a better word, trying to contain this point, and it succeeds in containing that point. Over here, as the function has x values approaching b from the left, from the negative side, the function tries to contain this point, and it succeeds. So there's an anthropomorphic way of thinking about it. This is a really good picture of what graphs of continuous functions look like at left-hand endpoints, right-hand endpoints, and interior points of the domain. Okay, so we got away with all of that without the epsilons and deltas, right? Well, whenever you say this limit stuff, there's epsilons and deltas lurking underneath. So there's epsilons and deltas in this, but we're reaching a stage now where we can sort of bury that level of detail. We can also use this terminology of continuous from the left and the right. At interior points, we might have a function that's continuous from the left, but not from the right. This point B could be an interior point and the function be graphed over here as well, and it might have some strange behavior over here to the right of B. But we could use this continuous from the left and right ideas at interior points as well, and we take the same definitions, the one-sided limit stuff. The trying to pass through a point and succeeding idea holds for these three types of continuity. You might argue at the endpoints, it doesn't really pass through, and go to the other side. So maybe tries to contain the point might be a more appropriate terminology at the endpoints, but it's the same idea of the function wants to have this value in a sense, and it does when it's continuous from the left, the right, or from both sides. In your many travels, I suspect you've heard of a function said to be continuous if it can be drawn without picking up your pencil. Now, for some technical reasons, there's a bunch of problems with that, but if we have a function that's continuous, if a function is continuous on its domain and its domain is an interval, I'm okay with that. If the domain is choppier, and it won't be in a calculus class, it might be in some higher level classes, but as long as the domain is an interval or union of intervals, I'm okay with this idea of can be drawn without picking up your pencil. And that's no worse than having it trying to pass through points. And it's legitimate in the setting of domains that are intervals. It's not legitimate in some other places. Let's look at exercise 2.5.4 to the supplements. All right, question is, state whether this function is continuous on the interval from -1 to 3. If not, where does it fail to be continuous and why? Okay, -1 to 3 is the domain of this function. -1 to 3 is the domain of the function. Let's talk, in terms of trying to pass through points or trying to contain points. Look what happens when x approaches the left-hand endpoint. We take x values that approach -1 from the left-hand endpoint. Then we get points on the graph of the function that would lie along this blue straight line part. So as we move along, this function's trying to contain the point -1, 0, as I put it. It succeeds because there's a blue dot there. So that one-sided limit exists. That one-sided limit equals the value of the function. It succeeds in containing that point. So the function is continuous from the right at -1. The limit as x approaches -1 from the positive side of k of x equals 0, equals what you get by plugging in -1. And that's one-sided continuity. How about the other side? Let's look at 3. Okay, now we'll take a limit as x approaches +3 from the negative direction. So I'm taking x values over here, close to 3, in terms of the limit, not equal to 3. But what happens at 3 matters now because we're talking continuity. And sure enough, if we look at it anthropomorphically, we get points that lie along this straight line segment, and that function wants to contain this point, and it does. So this function is continuous from the left at 3. The limit as x approaches 3 from the negative side of k of x equals, this is the point 3, 2, so the limit is 2. And in fact, that's what you get by plugging in x equals 3. So continuity from the left. Okay. How about on the interval from -1 to 1? Take any x value in this open interval from -1 to 1. Stay away from the endpoints, -1 and 1. Take something strictly between there. Straight line segment, I take any particular c value between -1 and 1, excluding the endpoints. Then this straight line is going to try to pass through some corresponding point, and it's going to succeed. So thinking anthropomorphically, we've got that k is a continuous function for all such points. You can evaluate a limit as x approaches c for the function by substituting x equals c in. Tries to pass through the point and succeeds. Same thing happens for x values between 1 and 3. Look at the graph of y equals k of x on the interval from 1 to 3. Again, it's a line and strictly exclude the endpoints. Straight line segment, same story. Any particular x value, the function tries to pass through a point and it succeeds. So continuous at each of the interior points in the interval from 1 to 3, the limit as x approaches c, two-sided limits again, is k of c. You can evaluate these limits by substituting in, and that's really what continuity is. More of that in a second. Okay, so that took care of everything except for 1, and obviously there's something wrong with continuity at 1. What happens when x approaches 1 from the left, from the negative side? Let's see, if we take x values close to 1 and on the negative side of 1, to the left of 1, we're getting out function values up here. The function from this side is trying to contain this point, what's this, 1 3/2? Say 1 3/2. It fails, so the limit exists, but we don't have one-sided continuity at this point, if you like. What happens when we let x approach 1 from the positive side? Then we're looking at x values over here. We're getting points along the function here, and the function's trying to contain this point. In fact, it does. We could say at the point 1, we have continuity from the right. The one-sided limit actually equals the function value there. We don't have continuity from the left because the limit is, what, 3/2, I guess, and the function value at 1 is actually 0. But in terms of two-sided limits, the two-sided limit, it doesn't exist. The limit from the left is 3/2. The limit from the right is 0. Those are different. We had a theorem that said two-sided limits exist when one-sided limits both exist and are equal. So the two-sided limit doesn't even exist here. Continuity means the limit exists and some other stuff. The function tries to pass through a single point and succeeds. There's not a single point it's trying to pass through. When we look at values of x near 1, I get 2 different points and we got a problem. And obviously that's not what I want to call a function continuous at 1. We'll classify this as a jump discontinuity here shortly. So where was the function continuous? Everywhere between -1 and 3 except at 1. So we'll write it as a union of 2 intervals and take the 1 out. everything between -1 and 3 except for 1 in interval notation written like this. Back to the notes. Okay. Speaking of continuity and limits, section 2.2, we dealt with limits by factoring, canceling, and substituting. I gave it a little acronym, FCS. So a reasonable question is, when can we evaluate limits by substitution? And what we had when we did this factor, cancel, substitute stuff is we couldn't substitute initially, probably led to division by 0. So we canceled, we factored, we canceled the offensive thing that gave us 0 in the denominator, and then we substituted in if we could. Well, when can you substitute in? When can you evaluate limits by substitution? Well, if there was an easy answer, we wouldn't have gone through all that epsilon delta stuff. But in hindsight, and be very careful on the logic with this, we can now, in hindsight, observe that a limit, one-sided or two-sided, can be evaluated by substitution, the evaluation of limits by substitution, when the function is continuous at the limit point. But that's what the definition of continuity is. Why didn't we just say this before? Well, look what we've done. We define limits in a very tedious way. Sometimes we substituted. We substituted when we had polynomials and when we had rational functions that didn't give division by 0. More generally, we could have said you can evaluate limits by substitution when a function is continuous. But what does continuity mean? Well, we define continuity in terms of limits. So you can't have it both ways. You can't define limits using continuity and then define continuity using limits. So that's why it's been as complicated as it's been. No circular reasoning allowed. What we've seen really is, by definition, a function is continuous when the limit as x approaches c of f of x equals f of a limit as x approaches c. Which of course is just C itself inside. So we said continuity was when the limit can be evaluated by substitution informally. Symbolically, it's written up top. We could do the same type of thing for one-sided limits, but this may serve you well at some point in the future. A function's continuous if you can pass limits in and out of the function. That is, if the limit as x approaches c of f of x equals f of the limit as x approaches c. Or f of the limit equals the limit of f. So you can take limits in and out of that function. That's what continuity at point C really means. We know a pretty good amount about limits at this stage. We can use the limit properties of polynomials, it's given in theorem 3.2, rational functions, given theorem 2.2, rational functions, given in theorem 2.3, to show that these functions are continuous on their domains. Well, a polynomial, nothing goes wrong there, domain is all real numbers. Rational functions, ratios of polynomials, well, you might have division by 0 at some x values. Well, those x values, they ain't in the domain, so you have to stay away from those. Stay away from those, consider the places where you don't get division by 0 and rational functions are continuous there. Here's a little claim we'll deal with here shortly. The 6 trig functions are also continuous, and we'll establish this below. Let's go ahead and give it a name. Right now, these claims about continuity, we're good on polynomials, we're good on rational functions, straightforward to show that. We're not so good on the trig functions just yet, but we'll get there. So let's go ahead and take this as given now, though I do owe you details. Make the claim in theorem 2.5.a that polynomials, rational functions, and the 6 trig functions are continuous at every point of their domains. Polynomials, the domain is all real numbers. Rational functions, the domain is where you don't get division by 0. Trig functions, see, sine and cosine are defined everywhere for all real numbers. Tangent isn't defined at pi halves, 90 degrees, or odd multiples of pi halves, and so forth. Sines and cosines are defined for all real numbers. The other 4 trig functions, tangent, cotangent, secant, cosecant, there's places where they're not defined. So their domains are not all real numbers. More of that when we need to deal more hands-on with the other trig functions. All right, so what we're going to do so we can test a function for continuity more cleanly, more rigorously. Without this, it tries to do stuff. We're going to break the definition of continuity into a three-part checklist of requirements for continuity. We'll treat interior points and endpoints of the domain differently, like we did in the definition. Okay, so we have the following tests for continuity at the three kinds of points we'll deal with. An interior point, which we'll deal with probably most often, a left-hand endpoint, and a right-hand endpoint of the domain of function f. So the claim is, part A, a function is continuous at x equals c, an interior point of the domain of the function, if and only if the following three things hold. F of c exists. In other words, f is defined at x equals c. The limit as x approaches c of f of x exists. All right. You know what that means in horrible detail, in fact, at this stage. And thirdly, those two things are equal. The limit equals the function value. If you like anthropomorphic ideas, part 2 says the function tries to pass through a point because the limit exists. And part 3 says it succeeds in passing through the point c f of c. F of c existing by part 1. So this is really the anthropomorphic thing written in more mathematically meaningful symbols. And the other two parts will be similar, except we'll deal with endpoints, and so we'll deal with one-sided limits instead of two-sided limits. A function f is continuous at x equals a left-hand endpoint of the domain of that function, if and only if the function's defined at that left-hand endpoint. The limit as x approaches a from the right, you approach a left-hand endpoint from the right, the limit exists, and the limit equals the function value. At right-hand endpoints, say b is a right-hand endpoint of the domain, same kind of thing. Function's defined at b, the limit as x approaches b from the left, from the negative direction, exists, and the limit equals the function value. So the three of these, I don't think the book actually states the last two explicitly, but let's do it in the notes. The three of these are simply the definition of continuity written out in a step-by-step process we can use to check a function for continuity. So let's take this piecewise defined function and check it for continuity at 0. F of x equals x when x is negative, 0 when x is 0, and x squared when x is positive, piecewise defined function. So we want to check continuity at 0. All right, we'll have to do it in terms of limits. Since it's a piecewise defined function, we'll probably have to break it into one-sided limits. So let's look at the solution to that. All right, so continuous at x equals 0. First off, the domain of the function is what? So it's like all real numbers. It's defined for all real numbers. I only hesitantly mention this. How many functions are we dealing with here? Or one function here, ain't there? There's one function. Its name is f. It's got 3 pieces, but it's one function. Which piece are you going to use? Well, that depends on the x values. X equals 0 is an interior point of the domain. It's defined for all real numbers. What happens when you plug 0 in? Which piece do you use? If x equals 0, we use this piece. So when we put 0 in, we get 0 out, because that's the definition of the function at 0. So we need to check to see, if we're talking continuity at 0, we need to see if the function exists at 0. Check. We need to see if the limit exists. And then we'll need to see if those two things are the same. To address the limit as x approaches 0 of f of x, x is close to 0, but not equal to 0. Which piece do you use? Not this piece. If I'm having a limit conversation, as x approaches 0, it doesn't matter what happens at 0. That still holds for limits. So do you use this piece or this piece? Well, I don't know. If all I know is that x is close to 0. because x could be close to 0 and positive, in which case we'd use this piece, or x could be close to 0 and negative, in which case we'd use this piece. I don't know with a regular old limit, but I'll know if we do one-sided limits. So let's use the relationship between one and two-sided limits. Theorem 2.6 is for the record. And let's consider a limit as x approaches 0 from the negative side of f of x. All right, so this means x is close to 0 and a little bit less than 0. It's negative. The little negative up there doesn't mean x is negative in general. It means what we're dealing with is x values on the negative side of this. Well, this is 0 this time, so it does, in this setting, it does mean that x is negative. So we'll have little negative numbers. Which piece of x do you use? Of f do you use? What does f look like when x is a little negative number? Negative, this piece. F of x equals x when x is less than 0. Okay, so we'll take f of x and replace it with x. That's what you do when these are the x values less than 0, which they are in this one-sided limit. That's why we had to look at one-sided limits. And the limit as x approaches 0 of x is simply 0. Plug the x equals 0 in. If you like, x is a polynomial. Theorem 2.2 lets you evaluate the limit by substitution. We'll get a lot of mileage out of Theorem 2.2. How about a limit as x approaches 0 from the positive side? Okay, now x is close to 0 and positive. What does f of x look like? This piece, or this piece? Close to 0 and positive. This is what the function looks like when you input positive values. We're inputting positive values where we replace f of x with x squared. Now we've got a limit as x approaches 0 from the positive side of x squared. That's a polynomial. We can evaluate limits by substitution, two-sided or one-sided. We said at some point Theorem 2.2 holds for one-sided limits also, so we should comment that. So we've got the one-sided limits as x approaches 0 from the negative and the positive side are both 0. That tells you, Theorem 2.6, since the one-sided limits are the same and they're both 0, the two-sided limit exists and it's 0. Okay, so all of that was to check the second part. The limit as x approaches 0 of f of x does exist. And by the way, it equals 0. Oh, and 0 is the value of the function at 0. So the limit as x approaches 0 of f of x is 0. It's f of 0. That's the third part of the test for continuity. So f is continuous at x equals 0. So yes, it is continuous. Back to the notes. We'll define several different types of discontinuities as follows. We'll have pictures of these, and a couple of them are easy to test, and one of them is not so easy to test. A function f has a removable discontinuity at x equals a if f of a can be redefined in such a way that f is continuous at a. All right, this is when you're going to have a graph that tries to pass through a point, okay, that means a limit exists, and fails for whatever reason, fails to pass through the point. That's a function with a removable discontinuity. Function f has a jump discontinuity at x equals a if the limit as x approaches a from the left and the limit as x approaches a from the right both exist as finite numbers. We'll talk about infinite limits here in the next section. Not that. The limits exist, but they're different. So from one side it does one thing, from the other side it does another, and it'll have a little gap in the graph. That's called a jump discontinuity. We saw an example of this earlier in one of the examples. That first example from this section, the k of x function had a jump discontinuity at x equals 1, didn't it? The limits were different from the one side, from the left and the right. A function has an infinite discontinuity at x equals a if it's defined on an open interval containing a, except possibly at a itself, and it's got a vertical asymptote at x equals a. Do you know what a vertical asymptote is? Don't take this the wrong way. You don't, because it involves some infinity stuff, which means it involves some limit stuff. You've got an informal feeling for what a vertical asymptote is. You don't have a formal feeling for it because we hadn't defined it in here. It requires limits to formally define. But I'm confident in your knowledge of vertical asymptotes enough to say, infinite discontinuities are where you have vertical asymptotes of the graph. I teach this senior level analysis class, or used to quite often. In that level of class, they break discontinuities into 3 classes: removable discontinuities, like we had, jump discontinuities, like we had. And then they take everything else and they just lump it together into a 3rd category called a discontinuity of the 3rd type. We'll mainly concentrate on removable discontinuities and jump discontinuities. One example of a discontinuity of the 3rd type is this infinite discontinuity as we defined up here. There's others, as we'll see in the following picture. The book considers what they call oscillating discontinuities, and that's what we've got in this last picture here. All right, well, let's go through and excuse me, analyze these at x equals 0. At x equals 0, what's up with this function y equals f of x? It's nice and continuous. It anthropomorphically, it tries to pass through the point 0, 1, and it succeeds. That's really informally, that's what continuity is. How about this one? As x approaches 0, this function tries to pass through the point 0, 1, and it fails. So it's not continuous at 0, but it's got a removable discontinuity, because we could define this function to be 1, redefine it, to be 1 at 0, effectively plugging up this little hole and removing the discontinuity. That's the reason they're called removable discontinuities. This one, same thing. Tries to pass through this point and fails, so it's discontinuous at this point. It doesn't contain the point 0, 1, it actually contains the point 0, 2. Could you fix it? Could you remove the discontinuity? Yeah, I'd take the function at 0 and redefine it to be 1, not 2, effectively moving this blue dot down here so it plugs up the hole. And then we would have a nice continuous function like we have in part A. So these two have removable discontinuities. It's removable in the sense that you could redefine the function at a single point and create a continuous function that would look like this in both cases. Here, hopefully you can see this. It's a function that's 0 for x negative. It's 1 for x positive, and at 0, it takes on the value 1. Of course, this has a jump discontinuity. Why is that a bit more quantitatively? Because the limit as x approaches 0 from the negative side is 0. Coming in from the left, it wants to contain this point, 0, 0. It fails. It's not continuous from the left, for one thing. But the one-sided limit exists and is 0. From the other side, it wants to contain this point, 0, 1. In fact, it does. The function is continuous from the right because the point's up here on this right-hand piece, effectively. Not continuous from the left. If I talk one-sided continuity at an interior point of the domain, which is what we have at 0, but in terms of regular old two-sided continuity, 0 is an interior point of the domain. So it's not continuous at 0. The left-hand and right-hand limits, they're different. From the left, the limit's 0. From the right, the limit's 1. And that's what you have when you have a jump discontinuity, aptly named, given the picture. Here, they've graphed, let's make it a little bit bigger, they've graphed y equals 1 over x squared. This has a vertical asymptote at 0. Thinking formally, we'll think formally here in the next section about these kind of things. But when x is a little number, x squared is a tiny number, and 1 over that is a huge number. So when we put numbers in close to 0, we get out huge positive numbers, positive because of the square. Even if I put in little negative numbers, square it, I get something positive and it's tiny, and the reciprocal is huge. So vertical asymptote, wink informally at x equals 0. Formally, we'll talk about vertical asymptotes in the next section. Vertical asymptotes are definitely an idea properly from the realm of calculus, even though you've probably seen it in pre-calculus. So this has an infinite discontinuity at 0. And this is what the book called an oscillating discontinuity. An oscillating discontinuity, they're taking the sine of 1 over x. Okay, so what's going to happen when x gets close to 0, this 1 over x thing starts getting really big. So when x gets close to 0, think of x moving along the positive x-axis towards 0. This sine function is going to take the reciprocal of those x values and see that 1 over x getting huge. It's changing quickly. As x travels closer to 0, 1 over x gets bigger and bigger. Well, that sine function, it's going to oscillate every 2 pi radians. Well, it's going to run through 2 pi radians awfully quickly when x moves just a little bit for x close to 0. So what the graph does is it oscillates faster and faster and faster and faster and faster and faster and faster as we get close to 0. And there's something like a mirror image over here on the right. There's a symmetry to it, I probably should say. But we see behavior, something like that. That's a discontinuity. The limit doesn't exist. We've talked about these kinds of graphs as having limits that don't exist at 0. Does the function get close to anything particular? Yeah, everything between -1 and 1 it gets close to, just doesn't stay close to it. There's not a single point that the function tries to pass through, if you want to think about it anthropomorphically. The limit doesn't exist. Well, dude, if the limit doesn't exist, the function can't be continuous at that point. So there's some examples of discontinuity. The ones we're really most interested in are removable, these two, B and C, and jump discontinuities. These others we'll just throw into the bin of other kinds of discontinuities. We don't have a way to deal with vertical asymptotes yet. We will in the next section. And we'll probably never analyze these oscillating discontinuities beyond just looking at pictures. Okay, and there's a caption for that image that describes each of those. Let's talk about the removable discontinuity stuff a little more. If a function has a removable discontinuity at a point, then we can redefine the function at that point in such a way as to create a new function which is continuous at that point. This new function is called a continuous extension of the original function. Okay, let's look at the discontinuities of a couple of functions. These are, let's see, one's an example from the book and the other is an exercise. This continuous extension thing, going through the material in the order of the book. We'll see this really illustrated at the end of the section. Right now, let's look at the greatest integer function first, and then this function, absolute value of x over x. Okay, so consider the greatest integer function. If you like, it's the rounding down function. I made the image kind of small here to get it on the slide. Sorry about that. G of x, greatest integer function. It's also represented with these little brackets. Notice there's little notches on the bottom and not on the top. It's the rounding down function. So when I take a number between 0 and 1, it's rounded down to 0. When I take a number between 3 and 4, it's rounded down to 3. At 4, the function jumps up to the value 4. Take a number between 4 and 5, 4.5, gets rounded down to 4. That's the reason you get these little steps. Sometimes it's called a step function. What's up in terms of continuity? Well, if you'll look at a limit from the left and the right at each integer value, that's where these little gaps are. If we take a limit, say for n an integer, we take a limit as x approaches n from the negative side. If n equals 3, I'd be taking x values here close to 3 and less than 3. Well, we're getting out for such values 2. So when I look at x values close to n and less than n, like n.999, we're going to get n minus 1 out. They're close to n, see, close to n and less than n. I did that wrong. It'd be like n minus 1 plus 0.999. Probably better to take specific numbers. What happens? Things get rounded down. Since this is strictly less than n, it's a limit, the rounding down function will produce the value n minus 1. If we come in from the other side, here I might be approaching 4 from the positive side. So I'm getting out, for numbers close to 4 and a little bit bigger than 4, I'm getting out 4, 4, 4, 4. I get out 4. It's a constant function to the right. And we get out n from that side. So from one side you get out n, from the other side you get out n minus 1 because there's a gap in it there. This is totally a jump discontinuity. So these have jump discontinuities at the integer values. Limits from the left and the right differ by 1. It's got a gap of size 1 at those integers. Now, if I choose anything between n and n plus 1, excluding the endpoints, the behavior of that function there is just a straight line segment. Forget the endpoints. It's a straight line segment. At those points, then we can say the two-sided limit exists. It tries to pass through points and it succeeds. It's actually a constant function on those kinds of intervals. We can justify saying then that the limit exists. This example 2.3.3b justifies that. And it equals a function value. If you like, anthropomorphically, on the little segments there, it tries to pass through points and succeeds. It's the endpoints that cause the problems. So it's continuous, except at the integers. So we've shown at integer values, it's got a jump discontinuity. Everywhere else, it's okay. So continuous on non-integer values, jump discontinuities at integer values. Let's look at the function f of x equals the absolute value of x over x. All right, if x is positive, then I can drop the absolute values and we get out 1. And when I say positive, I'm excluding 0. Of course, x can't be 0. If x is greater than 0, then f of x is 1. If x is negative, if x is less than 0, then the numerator is positive, the denominator is negative, the magnitudes are the same, and we get a negative 1 out. So we've got a function that's 1 for x positive and negative 1 for x negative. Let's go through and analyze it algebraically, and we'll draw a picture here in a second. So if c is greater than 0, then the limit as x approaches c of f of x. What's f of x look like? When I input positive values, it looks like 1. It is 1. Limit as x approaches c of 1 is 1. Does that equal f of c? Limit exists. Does it equal the function value? If I plug in c where c is positive, what do you get out? You get 1 out. So it is f of c. For c less than 0, what does f look like? Put negative numbers in. The function's negative 1, and that's the function value. So we've got, for c positive and c negative, this function is continuous. Test for continuity. F of c exists, the limit exists, and the limit and the function values are the same. I had to consider 2 cases because this is effectively a piecewise defined function. It comes in 2 pieces, a piece for x positive and a piece for x negative. But we went through the 3 pieces of the continuity test. Function exists, limit exists, and they're the same. I had to do it twice because of the 2 pieces. So this function is continuous for x not equal to 0. We only considered x positive and negative up here. All right, what happens at 0? Well, at 0, let's take limits as x approaches 0 from the left and the right. When x is negative, I know that function is negative 1. We get out a limit of negative 1. When x is positive, I know that function is positive 1. We get out a limit of positive 1. So the limit from the left is negative 1. The limit from the right is 1. Both of those limits exist, but they're different. That's a jump discontinuity. What's the graph look like? There's what the graph looks like. It's 1 for x positive. It's negative 1 for x negative, and it's undefined at 0. And sure enough, look at the graph. It's got a jump discontinuity at x equals 0. Let's look at another one. Yeah, here's a continuous extension. Define h of 2 in a way that extends this function to be continuous at t equals 2. Okay, h of t is a rational function. Is it continuous at 2? Let's check using the test for continuity. Is it defined at 2? No, we got division by 0. This is a rational function that's not defined at 2. End of story. That function is not continuous at 2. Does the limit exist as t approaches 2? If it does, then maybe we can fix it. We can create a continuous extension of it, is the right words to say. Limit as t approaches 2, t squared plus 3t minus 10 over t minus 2. Factor the numerators, t minus 2, t plus 5. Usual, FOIL backwards. FOIL this, you'll get that back. I trust you can do the factoring of a quadratic of this form. We've got t minus 2 in the denominator. Can you cancel those t minus 2s? In a limit, you can. Says who? Dr. Bob's limit theorem justifies the cancellation. We've factored, we've canceled. T plus 5 is a polynomial, so you can evaluate the limit by substituting t equals 2 in theorem 2.2. We factored, we canceled, we substituted. It's back to that. Okay, so the limit exists, and it's 7. The function doesn't exist. Well, why don't we redefine the function at 2 to be 7? H isn't defined at t equals 2, so H has a removable discontinuity at t equals 2. Redefine H of 2 to be 7. And this is the continuous extension of this function. It'll be continuous everywhere else. I mean, it's a rational function. The only place we've got a problem is at 2, and we can fix that problem for this function by setting the value of the function at 2 to be 7. So this is a continuous extension of H. The limit exists, it's 7. With this new definition down here, now the function at 2 is defined, and its value equals the limit. The value of the function is 7, and the limit of the function is 7. Redefining it, right? Now, arguably, using H for both of these is a little misleading. This is a new function. This is a continuous extension of H. It's not really H itself. H of 2 is not defined. Following the book's notation on this, I don't think that's too bad. All right. Theorem 2.1, limit rules, allows us to establish a bunch of continuity, sort of suggested by some of the things we've already seen. If functions f and g are continuous at x equals c, then the following combinations are also continuous at x equals c. So continuity means, by definition, you can evaluate limits by substitution. That's how you know polynomials are continuous. That's how you know rational functions are continuous on their domains. I've claimed trig functions are continuous on their domains, and I owe you some details on that. We already know that the limit of the sum is the sum of the limits. Okay, well then that has the implication that if f and g are continuous at x equals c, then so is f plus g, and f minus g, and f times g, and a constant multiple of f, and f divided by g, assuming you don't get some division by 0. It's the first one that comes with an additional disclaimer. F to the nth power, where n is a positive integer. The nth root of f. Okay, now this one I'm going to be worried about maybe square roots and negatives, so this will need a little more justification. The nth root of f is continuous at x equals c, provided the nth root of f is defined on an open interval containing c, and n here also is a positive integer. What about the, where's the except possibly at c thing? Well, this ain't a conversation here about limits. This is a conversation here about continuous functions. So here, it does matter what happens at x equals c. What happens at x equals c is what the limit is, and that's the very definition of continuity. So that's the reason we've lost the except possibly c stuff down here in the last one. And the punchline really on this is, crudely put, I should be careful with this, a function is continuous if nothing goes wrong. What can go wrong? Division by 0, we explicitly said that, and square roots of negatives. We've kind of implicitly said that down here. Anything else go wrong? Yeah, if we deal with trig functions, there's some things that can go wrong. I can't take the tangent of pi halves. So that I have oversimplified. But roughly put, if I don't deal with trig functions, I only deal with algebraic functions, then you're good to go with continuity if you don't have square roots and negatives and you don't have division by zero. So that's sort of a big punchline. It's not formalized in here because it's too hard to get all the caveats and disclaimers out that would give you something useful. But wink, wink, crudely put, if you don't get division by zero or square roots and negatives, you probably got continuity for an algebraic function. Speaking of trig functions, exercise 2.5.72 has you prove that f of x equals sine x and g of x equals cosine x are both continuous at x equals c. We dealt with a limit earlier involving the sine function and the cosine function. All right, so let's look at that. In exercise 2.5.71, it is shown that f is continuous at c if and only if, so we're going to take this as given, the limit as h approaches 0 of f of h plus c equals f of c, which ought to make sense. That's likely to be a homework exercise. It's an odd one at least. If h approaches 0, then h plus c approaches c. So we could do a change of variables to establish this exercise, but we'll just take this as given. And showing this is equivalent to showing continuity. The instructions are use this, an example 2.2.11, in which case we show the limit as theta approaches 0 of sine theta equals 0, and the limit as theta approaches 0 of cosine theta equals 1. Both of those are in the notes. That was shown, I think that was shown with a sandwich theorem. Both of these were shown with a sandwich theorem, and they're in the notes. So use this classification of continuity, these properties of sines and cosines, and how sweet of them. They've given us the summation formulas for sine and cosine. The sine of h plus c is sine of h cosine c plus cosine h sine c. Here's a summation formula for cosine. Hopefully these look familiar, whether you remember them or not. I'm actually mildly impressed if you remember these. But these are the summation formulas for sine and cosine, and we're going to have some h plus c stuff inside a function. So that's the reason these are the ones to consider. Use all that information to prove that f of x equals sine x and g of x equals cosine x are continuous at all points x equals c. Their domains include all real numbers, by the way. All right. Well, let c be an arbitrary real number, arbitrary point. We want to show the limit as h approaches 0 of the sine of c plus h equals the sine of c. So we're going to fiddle with this until we get the sine of c out for the value of this limit. Okay, sine of c plus h, well, here's the summation formula for sine in terms of h and c. That's why we were given this. So substitute this stuff for sine h plus c, sine c plus h. Make the substitutions. All right. This is a limit of a sum. We can write that as a sum of the limits. Sum rule from back in section 2.2, I think it was. We've got some constants here. Now, h is a thing that changes. C is not changing. C was fixed up here as some number. So cosine of c, I don't know exactly what it is, but it don't care what h is doing. It's constant with respect to h. It's a constant. We can bring constants outside of limits. So bring that cosine c outside of this limit. Over here, the sine c is constant with respect to h. Bring that outside of the limits. Of course, you can't bring the h's outside of the limits because h changes. H approaches 0. But sine c, constant. Cosine c, constant. Constant multiple rule says you can bring those out front of the limits. All right, let's see. Limit as h approaches 0 of sine h. And I know what that is from the past. Limit as h approaches 0 of cosine h. I know what that is from the past as well. So we'll be able to substitute for these limits the values 0 and 1 respectively. Here's where we left off. We can associate for these 0 and 1 respectively, and we get the sine of c. So the limit as h approaches c of sine of c plus h equals sine of c. That exercise says that's a continuous function. C was arbitrary. This function is continuous for all x equals c. You're going to like this one if you like that one. It's the same puzzle. Limit as h approaches 0 of the cosine of c plus h. We had a summation formula on the previous slide for cosine functions. This is a summation formula. It's got a difference. Limit of the difference is the difference of the limits. Difference rule from theorem 2.1. Cosine c is constant. Sine c is constant. Bring those constants out front of those limits, just like we did before, constant multiple rule. Next slide. Rewrite what we just had. Limit as h approaches 0 of cosine h. Cosine, that's 1. Limit as h approaches 0 of sine h. Here it's written with thetas, but whatever, is 0. Plug in a 1 for that, a 0 from that, substituting in, justified by what was computed up here. That disappears. We're left with cosine c. And as before, that shows that the cosine function is a continuous function at arbitrary x equals c as well. So we got sine functions are continuous. Cosine functions are continuous. They're continuous everywhere. We just stated a theorem that said, theorem 2.8, quotients in particular. Quotients, when we stay away from division by 0, quotients of continuous functions are continuous. Awesome. Then the tangent, what's tangent? Sine over cosine? That's a continuous function on its domain. There's some places where that's undefined. Cotangent, which is cosine over sine, is continuous everywhere it's defined. So now, with this observation of continuity of sine and cosine, we can say all 6 trig functions, they can be written in terms of sines and cosines using products and quotients. So all 6 of those trig functions, based on what we have upstairs for properties of limits, they're all continuous on their domains. Not continuous everywhere, but continuous everywhere that they're defined. Tangent functions not defined at pi has, for example. Cotangent functions not defined at 0, for example. Upstairs is theorem 2.5.a, I called it. We made the claim that polynomials, rational functions, and all 6 trig functions are continuous on their domains, and now we've got justification for that. Okay, let's go ahead and cut the video there. Got a little bit more material to do and some more examples to work, but we'll come back and take care of that in a second video. We're more than halfway, so we're doing good. I'll see you shortly and we'll finish this up.